Uh, Good afternoon, all. My name is Nitin Tomar. I am a third year PhD student in the Department of Mathematics at IIT Bombay. Today, I welcome you all to join me in this session where we are going to discuss some problem about complex analysis. So, in today's session, we are going to discuss some definite integrals using the residue theorem. So, and this is one of the problem. Okay, admit. Okay. So the today mostly we'll be covering definite integrals using residue theorem. All of you must have studied residue theorem by now. We'll see one application of it. Good afternoon, Thangeshwaran. So, so today what we'll do, we will use residue theorem. We will use the residue theorem to compute some line integrals. To compute some real line definite or indefinite also real line integrals. And because I have to stick to the assignment due to the lack of time, I'll be solving some. So my aim is to solve these kinds of integrals. Okay, so the aim is clear, right? So we'll do step by step. So okay, let us be clear. So our aim is to compute this integral 1 plus x4. Okay, so for that we might need a result, which I am trying to write now. Suppose fz is defined in the upper half plane such that and mod of fz is less than 1 upon m upon mod z alpha for some alpha greater than 1 and m greater than 0, and this happens for all mod z large enough. Large enough means after a certain stage this happens. Okay, then then this limit r goes to infinity c of r f of z dz is 0, where cr is the semicircle. Where is the semicircle which I'm drawing now? Okay, given by, so if this is your, sorry, if this is your imaginary axis and this is your real axis. Let's say this is the semicircle. Oh, it's weird. Okay. Yeah. So I have to just a minute. So is the figure clear, all of you? So this is my r.
Yeah,
Yeah,
clear,
clear,
sir.
sir. Yes. This is my r. This is my minus r, and this is my curve CR. Okay. Now they say if so on this curve, as you keep on increasing your r, this semicircle will grow big, right? For example, for r equal to 1, this is this. For r equal to 2, this is this. So what does this say? If you keep on increasing your r, this limit, of so okay,
Upper
upper half
plane.
plane. Yeah, upper half plane it is. So depending on r, so this is a complex number, right? This integration over CR, it is a complex number, right? Depending on R. Now what they say that this limit will go to infinity. And how do you prove that? How do you prove that? This is easy. So you know the ML inequality, right? ML inequality. So okay, we have to show that this CR FZ DZ, this limit goes to infinity. So we consider its mod. Now you know this triangle inequality for integration. This is same as this. So at any stage, if some step is not clear, then just please tell me. Now it is given in the question that mod of fz is less than equal to m by mod z alpha for large R. Okay, this is m by mod z alpha mod dz, the CR. Large enough R. If you choose large R, large enough. Anyway, you have to increase R to infinity. So you can always choose R large enough. Okay. Now, what this will be? See on CR, what is the value of mod Z? On CR, what is the value of mod Z? It is R, right? Yes or
Yes,
no?
sir.
Hmm. So it is M R alpha. It is actually equal to M R alpha integration CR dz. Hmm? Now tell me what is the value of this line integration? This is just the okay.
Fire.
Fire.
No, this is a semicircle,
Uh,
right? Ah, exactly, pi r. That is why it has to be pi r. Yes.
yes.
So ultimately it will be m, or let us write pi m r 1 minus alpha. Correct?
Yes,
Yes,
sir.
sir. Or yeah. Sorry, alpha is greater than 1, so it should be in the denominator. Why? Because alpha is assumed to be strictly greater than 1. So it should go to 0 as r goes to infinity, yes or no?
Yes,
Yes,
sir.
sir.
Yes. Okay. So this you agree, right?
Yes, sir.
Yes, sir. Okay. So this was the result that we will be needing. Now the step, okay. Let us call this step 1 instead of result. Let us call this step 1. Okay. So step 2, I'm going to write few things. See, the aim is to compute this integral, okay, using the residue theorem. Using the residue theorem. So let this be I. Now we consider the function. We consider fz equal to 1 upon its complex version, okay. Its complex version will be z4 plus 1, right? Yes or
Yes,
no?
sir.
Yes, sir. Yes. Okay. Now what are the poles? Can anyone tell me? Okay, we'll go step by step. Again, see in this figure. Now it is. So what are the poles?
It has four poles, sir.
Very good. It has four poles, right? All the poles will be all those z. So poles of fz. So what are the poles?
E to the power something.
Z4 is minus 1, right? The poles will be where z4 plus 1 is 0. Yes or no?
Yes,
Yes,
sir.
sir.
So can anyone tell me the poles of this? So it has
Minus 1 raised to 1 by 4.
no, Darshana, that is correct, but can you solve that equation?
Sir, e to the power I pi by 2.
E to
I
the
pi
power,
by 4.
they will be, there will be four poles, that is correct, but what will be those?
Sir, e to the power I k by sorry, e to the power I k pi by 4.
Very
Uh,
good.
in
Where k varies from?
k equal to 1, 2, 3.
Yeah, 0, 1, 2, 3, right?
Yes, sir.
Darshana, is this step clear?
Yes, sir.
And who else are there today? Payal, Prakash, Rajesh,
Yes, sir.
Shiva Subramaniam, and Thangeshwaran. Okay. Personally, again, I all of you welcome. And Payal, since I think you're joining for the first time, so this is more like a discussion class. Be
Yes, yes,
open to
sir.
your ideas. Okay. We all are learning mathematics here, so feel free to interrupt and feel free to discuss. Okay. Doesn't matter how wrong it may be. After all, we are here for a reason. Okay. Yeah.
E raised to I k pi by 4 e raised to I k plus 1 into pi by 4 ऐसा नहीं होगा?
Sorry, Darshana, can you repeat?
E raised to I in bracket 2k plus 1
Okay,
bracket
okay,
over pi
okay.
by
Let
4.
me make it simple for you. Okay, Z4 is minus 1, right?
Yes.
Now, what is one value of minus 4? You know.
Yes.
What is the
Cos
one value? E pi I, right? This is the one
e
value
raised
that
to
you
I
know.
pi. हाँ.
So, what should be your Z? It should be E pi I
By
by
4.
4, or like, okay, let me write it like this. So, one of the value should be this, but you also know. Uh, have I done something incorrect?
We add 2k pi na sir.
No, no. 3 pi by 4. Have I done? Oh, I think this should be minus. Okay, let me write it like this. So 1 will be there, 3 will be there, right? And then I think plus and minus, right? Is this correct now?
Yes, sir.
Because if, see, this is also root, then ei 3 pi is also there, and e minus 3 pi I is also there. Darshana, now you agree? All of this has value -1, right?
Yes, sir.
So you just so I think, okay, so this step is clear. Now what are the poles that lie in the following, in the semicircle that we saw above? So our semicircle was this. So again we are going to choose that semicircle only. You know, I'll have to draw something bigger. Yeah. So this is the semicircle we saw, right? In the above. So this is -r, this is r, and this is cr. Yes. Now what are the two poles that lie inside this? So okay, let me complete the figure. This is the closed curve that we are going to take. Now I think one pole lies here, one pole lies here, right? So ei pi by 4. This is one pole that will lie here, right? Because theta is pi by 4, and pi by 4 theta lies in the first quadrant, right?
Yes, sir.
Yes, sir.
And another will be e iota 3 pi by 4, because 3 pi by 4 is again some theta that lies in the second quadrant. So only two poles are there in this closed contour. Okay. Now you see, I am writing something and you tell me whether I can write this or not. Can I write this?
Yes,
This
sir.
why? Because why can we write this? Can anyone? So we have proved this in first step, right? If something follows, then this limit is 0. So see, our f set was what? Our mod f set is 1 plus z4, right? Mod of this, and mod of this will be less than 1 upon mod z4. Yes or no?
Yes, yes,
Yes,
sir.
Yes,
sir.
sir.
Yes. So here m is, so if you compare, you know, so it m is 1, alpha is 4, right? In our
Yes,
case,
sir.
m is 1, alpha is 4, and f is well defined in upper half plane, right?
Yes, sir.
Yes, sir.
At least on this curve that I'm saying. So this integral has to go to 0, and it follows. This follows from step 1, follows from step 1. Now second is, so you see what I want to say is the following. Now, and uh, this is my curve C1. So can someone mute their mic? Someone's mic is open. Please mute the mic. Yes. Let this straight line be the curve C1. Now, what was I? I was minus infinity to infinity, dx by 1 plus x4. Correct? Now, can I say that this is actually minus r to r dz 1 plus z4, limit r goes to infinity? Can I say this?
Yes, sir.
Where z is x plus iota y. Because on real axis y will be 0, so dz will be z will be x and dz will be dx. Okay.
Sir.
Hmm. So this is clear, right? Now
Yes,
now
sir.
comes the residue theorem into the picture. So see C1 plus CR, this is a simple closed curve, right? C1 union CR means this. Okay, let us write plus. This is a semicircle, so semicircle is a simple closed curve, right? Yes or no?
Yes, sir.
Yes, sir. Yes,
Hmm.
sir.
And f is a meromorphic function.
Yeah.
Yeah.
So what does the residue theorem will tell you? The residue theorem,
2 pi
2
sum
pi
of the
sum of the
residues.
residues.
very
2
good. So
pi.
it
2
is
pi
2 pi I.
over.
Sorry, this just a minute. So this sorry, C1 plus CR FZ DZ, right? This will be what? This will be 2 pi I summation residues of F inside this C1 plus CR, right? Inside
Yes,
the
sir. Yes, sir.
curve. This is what residue theorem is all about.
Yes, sir.
Yes, sir.
Yeah. Now, inside the closed curve, can anyone tell me what are the residue? See, we have seen that only EI pi by 4 and EI 3 pi by 4. These are the poles, right? These are the
Sir,
simple poles. Just a minute. Simple poles of F inside C1 plus CR. Yes. Yes, please
sir,
speak.
what you write in the above line?
Sorry.
So what you write in the above line? Summation of residues of something.
F
I
inside
couldn't
the
understand.
residues. So, uh, so residue theorem says if you have a closed curve, simple closed curve, okay, then integration of this F over C will be the 2 pi iota times. You just add all the residue. Let's say this has some poles here, so you just compute all the residues corresponding to those poles and add them up and multiply them by 2 pi iota. Then this will be the integration of F over C, and this is precisely what we call residue theorem. Okay, Pyle?
Yes, sir.
So, for example, okay, let me just give you one very quick example. If I ask you F z, uh, like dz by z over the circle, unit circle, mod z equal to 1, you can directly say that you can compute it, but by directly by residue theorem, this is your circle, mod z equal to 1, and your fz is 1 by z. So there is only one pole at 0, and the residue of f at 0 is 1, right? Clearly it is 1 here. Residue is 1. The coefficient of 1 by z is 1. So this will be 2 pi I times the sum of the residue. Residue is only 1, so 1. So it will be 2 pi iota. So this is how you thought of as the residue theorem. Now, so next step is to compute the residues. Okay. So let z1 be, okay. So let z1 be this E I pi by 4. and Z2 be EI 3 pi by 4. So if you compute residue at Z1, how do you compute? And these are the simple poles, right? These are the simple poles you can see. So the residue will be this: Z approaches Z1 limit Z minus Z1 f of Z. Yes or no? Because it is a
Yes,
simple
sir.
pole. Yes.
Yes, sir.
Now what is this limit? You just write down the value. It is Z minus Z1 and 1 plus Z4. You know that numerator, it is a 0 by 0 form at Z1. So you can apply L'Hopital and it will be Z approaches to Z1. Actually for any I, na, like 1 or 2, it doesn't matter. I from 1 to 2. So it will be 1 upon 4Z cube, correct? If you apply L'Hopital.
Yes, sir.
Yes. Now the value will be 1 upon 4 Zi cube. Is this correct?
Yes, sir.
Yes. So we just have to compute these values 1 upon 4Zi cube. Okay. So this implies residue of f at Z1. What was Z1? It will be 4Z1 cube, but Z1 was EI pi by 4. So it will be EI 3 pi by 4, right?
Yes.
Or
Yes, sir.
better I write it as E minus iota 3 pi by 4. So I have done some calculations. So it will be 1 minus 1. You solve this. So it will be 4 root 2. Okay. And similarly, if you find residue at Z2 of f, which has to be for 1 upon 4 Z2 cube. Now Z2 was already EI 3 pi by 4. So it will be 9 pi by 4. Right? Yes. So if you compute it, it will be 1 minus iota by 4 root 2. Okay. These two calculations you have to done. So where are we now? So hence this implies integration C1 plus CR fz dz. It is 2 pi iota and sum of these two residues. Can anyone tell me the sum of these two numbers? The sum of residues? So it will be 1 minus 1 minus iota 4 root 2 plus 1 minus iota 4 root 2. Correct?
Yes, sir.
Minus 2i upon 4 root 2.
Yes, minus 2I upon
4 root 2.
4 root 2 and 2 pi iota
2
times.
pi I. Yes.
2 pi iota times minus
Minus
2I
2i
4 root 2.
upon 4 root 2.
So can I say that this will be pi by root 2?
Yes.
Correct? Now this is for all R, right? See on the now if like if you consider this integral, what is this? This is C1 fz dz plus so C1 was minus R to R, correct? C1 was minus R to R. So let us go back to the figure. C1 was minus R to R, you can see, and CR was the semicircle arc. So this will be CR plus fz dz pi by root 2. Now as you can see, this RHS, this is independent of R, right? Yes or no?
Yes, sir.
This
Yes, sir.
RHS, yeah. So as R goes to infinity, it will become minus infinity to infinity fz dz,
Yes.
which is nothing but dx upon 1 plus x4,
Yeah.
correct?
Okay.
And this will be limit r goes to infinity cr fz dz, right? And all of this has to be pi by root 2. But this we have proved is 0, right? This limit.
Yes, sir.
So finally what we have is the following, that minus infinity to infinity dx 1 plus x4 is actually pi by root 2. Is this clear to all of you?
Yes, sir.
Yes, yes, sir.
And this was done because of residue theorem. I hope this is clear. So do you have any doubt in this? Please ask. I am giving a few minutes. Meanwhile, I open the assignment. So any other problem, any problem in this line integral? Please tell. So if you have any other problem in this line integral, then I request you to please ask.
Sir, please go to the last page.
Okay, okay, I'm going. Yeah, this one.
Yes, sir.
Hmm. Yes. What is the doubt? Uh, don't write it down. I will share. Okay. I mean, you can write, but anyhow, I'll be sharing. Okay.
Okay, sir. Thank you.
So you know the link pile where it is shared.
Yes, sir.
So then you just download it from there. Okay. Yeah. So
Okay, sir.
let me open the assignment. So these are your lecture notes, I guess. Mm, so this. So this is your assignment, right? Can you see the assignment?
Yes, sir.
Okay. So the question is, all of you can see, or should I zoom it more? Okay, let me do it here. Uh, Image, cancel. Yes. Mm, crop. So now can you see?
Yes, sir.
Okay. Yeah. So this is your question number one. Yes. So if f is a meromorphic, oh, I should rather do like this. If f is a meromorphic function on omega, and z naught is a point in omega, then which of the following statements are true? The answer is given, okay, in the green. So first option is, if the residue of a function f at the point z naught equals to 0, then z naught is a removable singularity. Is this option true? So okay, part 1, okay, let us part 1 के लिए. You consider fz equal to 1 by z square, okay. Now tell me the residue at point 0. Residue of f at 0. What is the residue?
Zero.
0. But is this function a remove? Is 0 a removable singularity?
No.
So first option is false. This option is false. Everyone get this?
Yes, sir.
Yeah.
Yes, sir.
Now second. So this is for part A. Part B. If z naught is a removable singularity, then the residue is 0. That is correct. Why? If z
In
naught,
removable singularity, no negative powers occur.
exactly, if z naught is a removable singularity of f, then in some neighborhood, in some disk around z naught, say of radius r, how can you write fz? You can write fz as a naught plus z minus z naught a1, correct?
Yes, sir.
So what is the residue here? There is no negative terms, right? So what is the residue at z naught? It is 0.
Zero.
Residue at z naught is 0. So this is correct. This option is correct. This option is correct. Now if g is another meromorphic function, then what is the relation between the product of their residue? Okay. So the first is this, is residue is, if residue of the product of function is the product of the residue, what do you think? Huh? Third option, what do you think? Residue of fg, should it be residue of f times residue of g?
No, sir.
Example.
1 by z into 1 by z.
No, 1 by z into 1 by z, it is 1 by z square. Yes, exactly.
Okay.
Yes, this works, right? Yes. Thank you,
But
Darshana.
sir, my question is residue fg z0 equal to g z0, residue f at
Just a minute,
z0.
एक minute, Darshana, एक minute. Let me write this first. Then residue of f at 0 is 1, which is same as residue of g at 0. But so their product has to be 1, but residue of the product, which is fz, which is, so this function will be 1 by z square. So this is residue of 1 by z square function at 0, which is 0. So this option is false. Now Darshana, yes, you were saying something.
Sir, can we say equality क्या है? Residue f g at z0 equal to g z0 residue f at z0 ऐसा लिख सकते हैं?
नहीं नहीं, residue is a number ना. See, this option is true. The next option, you read, then you know.
Okay. But some cases में ऐसा हो सकता होगा ना सर? g z0 को कॉमन निकालते हैं और रेसिड्यू f
हाँ, in
z0
some
फाइंड
cases
करते
it
हैं.
might be possible. In some cases it might be possible.
अच्छा, तो आप वो दिखा सकते हो?
हाँ, okay. Let us consider. So remark, okay, as remark. Anything can happen with the product. This is what I want to say. Okay, so this is my choice of f. This is my choice of g. This is my residue of f at 0. So I'm making a table, okay, and then product. Yeah. So if you choose your f to be z, and then let's say 1 by z square or 1 by z, then the residue here is 0, right? Here residue is 1. So but the product, and the product will have residue 0. So here equality is established, right, Darshana?
Yes,
Yes,
sir.
sir.
Yeah. If you choose it to be z and 1 by z square, then what will be the residue? 0 again. Here 0 again. But here then it will be 1, right? So again the inequality is not there. Equality is not there. So anything can happen. This is what I want
Sir,
to say.
ये
ये
रेसिड्यू और
रेसिड्यू और
स्लिप कैसे
स्लिप
फाइंड
फाइंड
करते हैं
करते
हम
हैं हम
लोग?
लोग?
Oh, you don't know how to calculate residue.
नहीं
नहीं
पता
पता
है
है,
1
वन
upon
अपॉन
z है
जेड
तो
है तो
रेसिड्यू
रेसिड्यू
f
What?
at
f at
z0
z0
is
is
limit z
limit z
tends to
tends to
z0
z0
z
z
minus
minus
z
Simple,
z
into
into
simple.
xz.
xz.
Yeah, that is one formula. But you know Lorentz series expansion and Taylor series. Lorentz series expansion, you know, right?
हाँ,
हाँ,
yes.
yes.
So let's say if you were to find residue of f at some z naught, and f is a meromorphic, and f has some pole, let's say it's a meromorphic function, okay? So you can write, how can you write fz in a neighborhood? In a neighborhood you can write fz as this, right? The positive part and the negative part, let's say a minus 1. Correct, Darshana?
Yes, sir.
Yes, sir.
Now residue, what is residue? Residue is this a minus 1, okay?
Yes, sir.
Yes, sir.
So, and if you look very closely, if it has a so this is the formula for residue, right? Its limit, the formula that you were saying.
Yes.
Yes.
Now you multiply it with z naught, then you'll see that this part will go to 0 and you will have a minus 1 left.
Okay.
Okay.
Okay, so yeah, is this clear, Darshana?
Yes,
Yes,
sir.
Yes,
sir.
sir.
Pile, you are saying something?
No,
No,
sir.
sir.
Okay, now see, for the fourth option, you know it is clear, right? You add two function, then you can split the limit, right? So what will be the residue of this? It will be limit, as Darshana said, it is this formula, fz plus gz, right? Yes or no? And
Yes,
then
Yes,
sir.
sir.
this limit you can split, right? This will be fz plus limit z minus z naught gz, correct?
Yes.
Yes.
Yes, sir.
And this is residue at g and this is residue at. So this option is correct. Now, suppose S is a compact set contained inside omega, then F has at most finitely many singularities. This option is correct. Why? See, if S is a compact set, okay, so, and F is a meromorphic function. So let us assume, okay, this needs a proof, the E part. So S is a compact set in omega. S is a compact set in omega in which f is meromorphic, and f, this m is for meromorphic, okay? Can I use this notation without confusing you?
Yes. Yes.
Okay. Now let if possible f has infinitely many poles. F has infinitely, the only singularities f can have is poles, right? Because f is a meromorphic function, and by the very definition a meromorphic function can have only finite can have poles as the singularity. So in the question it has been asked finitely many singularities, so any singularity will be pole only, okay? because f is a meromorphic function. So we are assuming on the contradiction that okay, uh, it has infinitely many singularities in S. In S, that is also important. Inside S. So this is inside S. In S. Okay. In S. Now S is a bounded set, and if it has infinitely many poles, every infinite points have a limit point in a bounded set. Yes or no?
Yes, sir.
Yes. So what you do, because it has an infinitely many poles, so we can choose a sequence of pole, right? Just choose arbitrarily anything. Let's say P1, P2, because it has infinitely many, so I can choose count at least countably many points, right? This countably many poles in S, correct? Yes or no?
Yes.
Now since S is bounded, actually it is compact. Compact means close also. So if that limit point is there, then it has to belong to S, right? Because every closed set contain all of its limit point, correct?
Yes,
Yes.
sir.
Yes. So there exists a P in S such that such that P is a limit point of P is a limit point of this sequence. Now what does it mean? What does it mean? You take any P, and in some neighborhood you'll have a Pn, right? You'll have some Pj, correct? Yes or no?
Yes, sir.
So but that cannot be possible, right? Which means f at z equal to p has a non-isolated singularity. Yes or no?
Sir.
Is this clear?
Yeah.
Because
Yes, sir.
non-isolated, why? Because you take any neighborhood of p, you will have one Pn, and Pn is a singularity. But this is a contradiction, right? Because as a singularity, f has only poles, which is an isolated singularity. Okay, is this correct? Is this clear?
Yes.
Darshana?
Yes, sir.
Yes, sir.
Okay. Darshana, you seem confused.
नहीं नहीं वो जो था ना रेसिड्यू एफ जी जेड जीरो।
और तुम अभी तक वही हो? बोलो उधर क्या
नहीं,
दिक्कत है?
हाँ इसमें राइट हैंड साइड में सर ऐसा है कि जी जेड जीरो इंटू रेसिड्यू एफ जेड जीरो,
हम्म
तो वो सही हो सकता है क्या?
हाँ, अभी तो एग्जाम्पल दिया ना कि सही हो भी सकता है, नहीं भी हो सकता है।
नहीं नहीं, आप सेपरेटली लिखते हो ना सर, रेसिड्यू एफ एंड रेसिड्यू जी, रेसिड्यू जी के लिए रेसिड्यू नहीं फाइंड करना है।
नहीं, प्रोडक्ट देखो ना, इनका प्रोडक्ट क्या आएगा? लेट्स से दिस इज एक्स, दिस इज वाई, सो एक्स वाई क्या है? इधर जीरो है, इधर जीरो है, तो ये तो सेम हो गए ना।
ओके सर, आप समझ नहीं रहे, ये रेसिड्यू जी जीरो है ना, वो मैं नहीं बोल रही हूँ, जी एट पॉइंट जेड जीरो, बस रेसिड्यू नहीं लेना है।
ओ, तुम ये कह रही हो कि
ये
इसकी
जो राइट
जगह
हैंड, हाँ जी जेड जीरो है बस, तो ऐसा हो सकता है क्या?
अगेन ऐसा हो भी सकता है और नहीं भी हो सकता है, तो वो तुमको चेक करना पड़ेगा, ठीक है? कोई भी
अच्छा
एनीथिंग एज अ स्टेटमेंट इज ट्रू इफ इट होल्ड्स फॉर एवरी फंक्शन, राइट?
हाँ हाँ, तो सभी फंक्शन के लिए चेक करना होगा सर।
एग्जैक्टली। When you
ओके
say
सर,
n is strictly less than n plus 1,
ओके
what do you mean by this statement? That every natural number follow this, correct?
ओके यस
If I say, you know, n is equal to n factorial, What would you say? Is it true?
No.
But with your logic, 2 equal to 2 factorial, then it should be, I mean, that doesn't, but it doesn't happen for any other.
Yes.
So if a statement is true, it has to be proved for every class of function. Okay, everything that is
Okay.
involved in the question.
Okay.
Okay. Okay. And so in this, I think, done. This we have already done, right? This we have already done. What should be the answer? 1, right?
Yes, sir.
Yes.
Because its answer was pi by root 2. So it has to be 1. Okay. So everyone can see the question? Yes. Now f is a meromorphic function on the complex plane and it is given like this. So okay. So it is half times 1 upon z minus 1 plus 1 by 2 square times 1 upon z minus 2 plus 1 by 2 cube. Now, what are the poles? What are the poles?
1/2.
No. Poles of f are 1,
Integers.
2, positive
Integers.
integer.
1, 2, 3. Natural
Pile,
numbers.
it's not 1 by 2, right? Is this clear to
Yes,
all of
sir.
you? Darshana, Payal, and Thangeshwaran,
Yes, sir, clear.
Prakash, I hope
Yes,
you.
yes, sir.
Yes, yeah. Because see, you can see that 1 upon z minus n is there, right? And these are simple poles, correct?
Yes, sir.
Yeah. Okay. And what is the, so what is the residue at any natural number? It is 1 upon 2n, right? Residue.
Yes, sir.
Residue, okay, okay, because there's some confusion, so I will write it as, if you in the power series expansion, in the Taylor series expansion, residue at f, residue of f at n will be coefficient of 1 upon z minus n. Okay. So if you let's say, like, in some neighborhood, that in some neighborhood of 1, you can stay very close so that it does not contain any other integer, right? Yes or no?
Yes, sir.
Yes, sir.
So every other element in the sum will be some analytic function, correct? This will be some analytic function. Yes or no? In this neighborhood, in
Yes,
this
sir.
in this neighborhood, let's say this neighborhood is n. Is this clear?
Yes,
Yes, sir.
So now when you try to write down in this neighborhood, what will be the series? It will be some a naught a1 z minus 1, something like this, right? Of phi z, because phi z is analytic, so it has Taylor series expansion. Yes or no?
Yes, sir.
Or you can directly, so what is the, so only this part, see, this part is there only, right, in the principal part. So is this clear, what I'm trying to explain here? Or you can directly use the formula. Okay, better to use formula in this case because it will be a little bit. So it will be 1 upon z, because poles are simple. So you see, like, so it will be z minus n. Correct?
The final answer is one. Is it right
Final
answer?
answer, abhi. So this residue will be 1 by 2n. Okay.
Yes, sir.
See, you just see the
NPTEL.
coefficient of 1
N-
upon z minus n. It is 1 upon 2n, right?
Residue of NPTEL.
Yeah. So, and so this sum will be nothing but 1 upon 2n, right? And going from 1 to infinity.
Yes, sir.
This is a GP.
Yes, sir.
So its sum will be first term, which is half, minus 1 upon the ratio. The ratio is half. So
Half.
it is half upon half, so it will be 1. So some of you were saying that it is 1, and that is the correct answer. Is this clear?
Sir, I have another approach to find the residue for this
Who is this?
function.
Say your name.
Subramanian.
Yes, yes.
Uh, just now we see that sum of the residue of sum of two functions is equal to sum of residue of the two functions. Using this, we can find term by term residues for this infinite series.
Exactly. Yes, yes,
We
yes.
have 1 by 2 plus 1 by 2 square plus 1 by 3 square, etc. This is a residue for this function. We sum it, we get the final answer as 1.
But see, that seems correct logically, but there can be one, because then it will be a. So you have to be sure about the convergence. Okay, that's it.
Yes, sir. Okay, okay.
Because it is an infinite sum. So because anyhow that argument will be valid because this series 1 upon 2n converges. Okay.
Oh, yes, sir. Yeah.
Yeah. So I think I'll finish here. If you have any doubt, please ask. So all other questions I was going through, they are not that difficult. Yeah. So this question, okay, let us do this question also. Quickly we can do some more questions. Hmm, yeah. So this question, can you see on your screen?
Yes, sir.
Now you know the Roche's theorem.
Please repeat again for me, sir.
So Roche's theorem, you know, right?
Yes, sir.
Yeah. So in this question, you have been asked to find the roots of this polynomial inside the unit disk z7 by 7 minus z5 by 3 plus 1 by 12 inside mod z less than equal to 1, mod z less than 1. Okay, is this clear, the question?
Sir, it is Roche's or Koch's theorem.
Sorry.
Sir, but I know it is Koch's theorem,
No.
but not Roche.
Roche's theorem has been done in the class in the last. I have seen the notes. Okay, so you please go through the notes. Uh, uh, what about the rest of you? Do you know Roche's theorem?